Okay, so today we're going to talk about something, I guess we can call it sampling distributions, I think is what I called it in the course outline. Technically, oftentimes these things are called probability mass functions, or probability density functions. I guess it really means roughly the same thing. This is stuff that you've ran into before, but not from this angle, let's say, that way. So, let's slow it. You can plot the probability of any given score for a variable. So, a variable is just some number whose values can take a whole bunch of different values. So, any given score has a probability, right? Probabilities range from 0 to 1, 0 meaning it doesn't happen at all, 1 meaning it's certain, right? The probability of all possible events is 1. So all the events together, the probability of all the events is 1. All of them put together. Right? Does that make sense? Right? That's all the possible events, all the possible scores.
100% or 1?
100%, right? 1 is 100%, because the probability range from 0 to 1. Yeah, so if you want to think of it in percentage terms, the probability, the percentage likelihood of all possible events is 100. Yeah, you want to think of it this way, the probability of a National Hockey League team winning the Stanley Cup is 1. I said a National Hockey League team, I didn't pick one. There are 31 teams, but a National Hockey League team will win the Stanley Cup this year. It's not like out of nowhere the Greyhounds will be allowed to. And for reasons that completely escape me, maybe an expansion team will win it. The Upside Down has become so weird.
It is.
Vegas Golden Knights, whose logo looks like a Cylon, if you've paid attention. Okay. So that means if we have a curve, because we can plot this, we can plot the probability of score, right? So just our picture, if it was in chalk, here's some chalk. If we could plot some score, the probability of some score, right? And it could be any value, it doesn't matter. If we somehow knew the probability of every single NHL team winning the Stanley Cup, which we don't, but if we did. Well, we could at the end of the season, it's all 0 for everyone, and for one team it's 1.0. The area underneath that curve, right at perhaps the Vegas Golden Knights, excuse me, I just threw up my mouth a little bit, would be 100%. Right? So any score, no matter what it was, we can alter it if we want to. And this probability on the x-axis, or the y-axis, and the score on the x-axis, the value of x. The area underneath that curve is 1. Because it's all the probabilities of every possible score. Does that follow? It makes some sense, right? Okay. So what about a die roll? Let's think of a classic statistics examples involve coins, dice, things like that. And I mean a regular die, not one of those 20-sided dies that people use who have no friends. It's a joke. I have friends who play Dungeons and Dragons.
You have to have friends to play Dungeons and Dragons.
Well, I don't know how you're defining friends, but yeah, maybe not social skills, but friends. It's a joke. It's a joke. Like I said, I've never played, but I have friends who play, and they seem like nice people. My daughter plays. She seems reasonable, so that's fine. So it's 0.167 because there's a 1 in 6 chance of any possible die roll. And if I had 0.167 times 6, I got 120. Right. Now those are bars, and they probably shouldn't be. They really should just be little points. Let's not get too mathematical here, because it's going to get pretty mathematical shortly. So let's not overload the math yet. Okay. Makes sense, yes? Okay. Now let's move over to everybody's favorite distribution, the normal distribution. We've all got a favorite distribution, I'm sure. I like a good Poisson distribution. Enjoy a good Markov process. Some of these are just for me. So this is a normal distribution. I believe I typed into Google normal distribution, and this was the first thing that came up in Google Images. But you've seen something like this before, such that this is a standard normal distribution because there's a mean of 0, and a median of 0, and a mode of 0. Very nice. Mode, the least interesting of all possible measures of central tendency. It's not one you see that comes up much. What's the mode? I don't know, nobody cares. And again, I'm making little jokes to myself that I'm editing it. And a whole thing about Depeche Mode there, that probably none of you have heard of them. I just can't get enough of those kind of jokes though. Nobody? See? Okay. So, this is the probability of any of these scores. That's what's on, it's not labeled that way, but that's what's on that axis. Like I drew over here in the, and we've got plus or minus a certain number of standard deviations. And in fact, you know these rules. You probably learned a rule that I think it's actually a Russian's name, but I always forget the name. I call it the 68, 95, 99.7 rule, such that plus or minus 1 standard deviation has 68% of the possible scores. So that means the area plus or minus 1 standard deviation is 0.68 of this, all the area underneath this curve. The area plus or minus 2 standard deviations is 0.95, 95%. Right? And the area plus or minus 3, which we have here, is 99.7% of the scores, or 0.997. That's the area underneath that curve. Okay? Sorry, I have to check something here. Okay, no worries. Wait, what was that? No, where express card search for? No. Oh, Netflix, okay. Question so far? Makes sense, right? The area underneath that curve, all the possible scores is 1. We get to almost all of them with normal distribution at plus or minus 3 standard deviations. You get 99.7 or 0.997 is the area underneath that curve. Move that over, put it there. So this is the most common, or at least the most useful for us, distribution. We talk about this all the time in statistics. It has certain characteristics to normal distribution. It's unimodal. And typically you want to describe distribution, you want to talk about the shape, the spread, and the central tendency. Shape, it's unimodal. It's symmetrical, and it's quote bell-shaped. And the standard normal distribution has a mean of 0 and a standard deviation of 1. Right? Question so far. Again, this is, I think, framing this before. 2026. Okay. So, why, you might ask yourself, why is this useful other than Dave wants me to know this, which is a perfectly valid reason to know it. Many variables are assumed to be normal in the population. Note that I said they're assumed to be normal. Very often they actually aren't. You'll get this a lot in intro stats textbook homework assignments. Right, you'll say something like, the average life of a light bulb is assumed to be normal. No, it really isn't. Any good factory makes it so it's skewed all the way it's skewed to the left, right? So it's negatively skewed. But they're not going to make it so it's, oh, so we have light bulbs. You don't buy those anymore. But a lot of things are. I think human height probably is. I think human weight probably is of adults. That seems fair. There are some very small people and some very tall people, but most people are somewhere in the middle. Plus or minus 68%, one might guess, or plus or minus 1 standard deviation, right? People often ask me, how are you doing? And I say, plus or minus 1 standard deviation. I'm right in the meaty part of the curve. I like to live there. I don't want to be either extreme. I would be really happy or really sad. I just like to be right in the middle where everyone lives. It's a sensible place to be. I try to be. I'm not saying I'm successful. Much better not to be fair. So we can actually use standard techniques to look at probabilities of scores because we have a distribution that we know a lot about. Okay? One of the interesting things here is that sampling distributions are wrong. And then we know that through the central limit theorem. Right? So sampling distributions, a sampling distribution of mean is normal. So if I was to put that sort of mathematically, the central limit theorem. If we think of x bar, the sample mean, as a variable, which is a very strange thing to think of because we've calculated it. But I've said before, numbers don't know where they come from. So the sampling distribution of the mean, in other words, if we took the mean of a bunch of samples and then plotted out the probability of those means, this is where it's sometimes a little hard for people to get their head around this, because we've got a sampling distribution. We have a population distribution which we don't know about. But we do have a sampling distribution, so we can take a sample mean of size, so take a sample of size 10, let's say, or generally, yes, of size n. And we do that a whole bunch of times. And then we'll take those scores, and those scores are means, and we plot the probability of getting those means, we end up with a normal distribution. If I was to flip a coin 10 times, what do we expect? How many heads do we expect? What's the expected value? 5. That's right. We would expect usually to get 5 heads. So let's plot out the average number of heads we get. And let's just do this as a thought experiment. You can do this yourself if you have some free time. Feel free. I'm not going to do it. But do this as a thought experiment. So let's just imagine we put 5 in the middle. We know that the expected value mu in the population should be half. Half the time we get heads, half the time we get tails. Right? So we should get 5 typically, the most common. Are we going to get 6 heads sometimes? Yeah, sure. Is it more or less likely than getting 5 heads? 50-50 chance, guys. Less. Thank you. That's 6. Do you think what's the chance of getting 4 heads? You think it's probably the same as getting 6. Does that follow? That does, doesn't it? Right? It makes some sense that just intuitively, don't worry about math right now. Just intuitively, we should get 4 heads as often as we get 6 heads when we flip a coin 10 times. Okay. What about 7? That's going to happen, isn't it? It's going to be less likely than 6, but it's going to happen. It's probably quite a bit less likely than 6. And 3, then, is going to be just the same likelihood. We're going to get 2 sometimes, or 8. Sometimes we're going to get 1 or none. Sometimes we're going to get 0. And exceedingly rarely, because this is a fair coin, we're going to get 0 or 10. It's going to happen, it's just going to be very rare. Very rare. It's going to be pretty rare. It's going to happen. Whoa. Wait. Look at that. That's pretty. And that's just intuitive. If you'd like, I can go back to my office. Oh, I can't. It's in my office that's been shut down due to construction. I could go get my graduate stats textbook and show you the proof of the central limit theorem, which would likely help no one, with me included. But in fact, it is the case that any sampling distribution of the mean, no matter what the parent population shape, doesn't matter what the shape of the parent population is, we can tell you what the sampling distribution will look like. It'll be normal. Holy, that's cool. It'll be normal, that's what the big N here means. It'll have a mean of mu sub x, meaning the average sample of the sampling distribution will be the same as the average for x. And the standard deviation will be sigma over the square root of n. In this case, we would 1.14. Did it run over the expansion, so yeah. Ever cool. It also says it'll be sigma over the square root of n, because once we get, let's think of it this way. The variance of this equals this. Variance of x bar equals sigma squared over n. So the bigger the n, sigma squared doesn't change. It's a parameter. Population parameter. We don't know it, but it's there. I can do it with a coin because there's a quick way to actually figure that out. But doesn't matter. Doesn't matter. Sigma squared over n.
What were you going to say, Dan? The bigger the n?
Well, the bigger the n. So let's say we start out with, well, we have the number here 10 times. With that distribution, again, just intuitively, would it not get tighter if we had more coin flips? Instead of doing 10 coin flips, we did 1,000. You're not going to expect a whole lot of times instead of, and you're not going to expect 600 coin flips out, or 600 heads that often. It's going to really tighten up. What if we were able to do all the possible coin flips that have ever or ever will be done. In other words, the entire population of coin flips, which is something that's like, whoa, wait, what? How am I going to do all the coin flips? Because you're magic and you're a god. Okay? It's not one of those interesting gods like an American Gods. You're the god of coin flips. We get all the possible coin flips. Then we get it again. We're going to get the same value every freaking time because we're not measuring the population anymore. We're not sampling anymore. We're measuring the population. As n gets bigger, the variance of x bar gets smaller. And in fact, as n approaches infinity, infinite number of coin flips, all the coin flips that will ever be done, ever, and will have been done in the past and the future. This is the worst episode of Star Trek ever. But Spock, what about all the coin flips? So, sigma squared over n. Let's get a little mathy. I'm going to write something down that you may have seen. I hope they still teach this. What's the limit as n approaches infinity of sigma squared over n? Remember limits? Remember you learned that? You thought, nobody's ever going to bring that up again. I just did! Ha ha! I had to do something to keep you. Not bad. I have been in this class since about 2002, when people cheated on a quiz. And I went, yeah, more than one. And I went into a whole thing about feeding me to a blind guy that cheated. I feel bad. It was great. Play the cards you're dealt, man. That's what I say. So, what happens to this quantity, sigma squared over n, as n gets infinitely large? What's going to happen to it? Anybody here remember doing limits in high school, first of all? Put your hand if you remember. Okay, so some of you remember doing limits. That's nice. So some of you remember your some high school math. Who here was told, don't take math anymore, you'll never need it, by their guidance counselor? That's great. That's wonderful. Way to go, guidance counselors. Sigma's a set value. It just gets smaller, and as n gets to be closer to infinity, what's that thing going to become? It's zero. It becomes zero. Because now we're measuring the whole population. So we have no variance in x bar because it's always the same damn value. Right? Keeping with the key point, which is that sigma squared is fixed, but n's getting bigger, and as a fraction, so the denominator gets bigger, and the top thing numerator is the same. I never can remember those things. By the way, less than greater than signs, I still remember as the alligator's mouth points towards the biggest piece of food. So, because I was taught that in grade 3. So, that thing gets huge on the bottom. The top is going to get so small that it's now zero. Ever neat? So I can show you the proof, but it doesn't help. But I think intuitively you see why this works. I hope. Okay, questions? I won't throw any chalk anymore for a while. I kind of like doing that now. I would never throw chalk at people. So let's think of just any distribution, any probability distribution. What's the probability of getting a score with this weird rectangular distribution that I've never seen in my life? Between 3 and 7. Well, it'd be the area between f at 3, all the functions, and f at 7. It'd be the area of that sort of house-shaped thing. Right? Does that follow? Excellent. So it's the area under the curve that we're caring about. It's the area under the curve. Is that the piece I threw? I mean, it really reflected backdrops. I shouldn't do that. I'm gonna hurt somebody.
Deal someone's nuts.
Yeah. We have a little eye joke thing, Chris and I, that we can do. Nobody else really in the room can do, so it's perfectly cool.
It's all fun and games.
Yeah, until somebody else. I'm sure you've never heard that before, right?
I use it all the time.
I'm sure you do. And then people feel uncomfortable?
That's
That's why you do it, right? Oh, yeah.
That's when you win.
I know, I think I told you the time that I was at a podcasting conference and I read this thing on a boat. We were on a boat. I don't know why we were on a boat. And there was a friend of mine, Brent, and he's got a really screwed up leg from some genetic disorder. And he calls himself a cripple. And I'm calling myself blind. And we were just doing it really loudly to see if it made people feel uncomfortable. It's the best. Oh yeah, it's the best. It's the best thing ever.
Especially when you don't really know somebody.
Oh yeah. Well, we kind of knew some of the people, but half of the people, there's a lot of people they've never met us. Yeah, it's the greatest thing ever. So that would actually be easy. Simple geometry, right? You go back and take a look at that shape. You got a square. I hope you know how to find the area of a square. I'm not showing you how. And then the area of a triangle. That's not that hard either, right? It's a half base times height, I think, right? So you could do that. Yes, if you were into that sort of scene. So that's pretty simple geometry. You could do that. In fact, it's pretty trivial. So if it's not a common shape, though, and the normal distribution, thinking about it, is not a common shape. It's a weird looking thing. Anybody here ever find out how to do, when you were like grade 4, they're showing you areas of shapes. They never said, oh, and also a Gaussian normal distribution. How do you calculate that? I don't know why your teacher would speak like this. I don't know what that was. Grade 4 teacher who talked like that would be, I don't know, a little odd. Any teacher would talk like that. Anybody here taking calculus? I think I asked that before. It's okay if you have it. I'm just curious. Nice. Tough. You take it in university or high school?
First year.
They used to make it. See, at Western, to do stats, you have to do math class. Now, there is a course called, Applied Linear Algebra for Social Science students, which is really easy. There's also Introductory Calculus for math majors that idiot brain over here took. Well, I'm smart, I'll take that. And it was great up until about March. And it was like, okay, you lost me. And that's when I have no idea what's going on now. That's the guy I told you about, Dr. Kochman, that had the...
I was going to say, is that what you just
told us to
used
get
for
7? Yeah. And I got up, he knew everybody's name in the class, 250 people. And we're literally doing this stuff, and I got up to leave, because it's like, I don't understand what's going on anymore. I thought I was smart. I'm here on a freaking scholarship. I don't know anything, right? First year. And he's like, Mr. Broadbeck, where are you going?
Oh.
And I said, I'm sorry, sir. This is no fault of yours. I have no idea what's going on. And you're wasting my time and I'm wasting yours. He goes, well then, good luck. He's the best. I did okay in the course because everything up till March was easy. It was a full year course. Got to March, it got really hard.
Did you pass?
Did you see
Oh
how?
no, yeah, I got an 80. Well, no, because I got like 100 and everything up till March.
So is it fair to say that you went and sought help afterwards?
No.
Oh. You
No, I tried. I kept trying.
Yeah.
I kept trying. I went to tutorials, TA said.
Yeah.
Some math graduate students trying to teach me stuff. I'm like, I don't know. I tried. But it just stopped making sense to me. It was like Taylor and McLaren series. And I kept looking at it like, well, I don't know what that means. It was things like area under a curve. Oh, I can do that. It's the integral of the function between 3 and 7. If you don't know how to do that, don't worry. It's not a big deal. Some of you, I can see smiles on some of your faces. Like, oh, right. I remember doing that. And then if it's a solid, you spin it. I could do that. It was when we got to these weird series. It's like, I don't understand. it suddenly felt like the whole course was suddenly being taught in an entirely different, it was like I was an alien from a stupid planet. You know, it's like, you know that episode of Star Trek? Make us go, Jordy. It was like that. Make us strong. We want to go. So, one could do calculus. So, you might say, I don't know how to do calculus. Oh, that's too bad. It actually is a shame. People should learn calculus because the basics of it are really beautiful. Math that describes the universe. It's very cool. So calculus is a neat thing to know. And I think, in fact, people should know some calculus just because it helps you understand some really basic things with the universe, which is a neat thing to know. Like, it's just cool. But, okay, so the normal distribution, so if you actually knew the function, it looks like this. Holy jumper. So f of x, so it was y equals, I'm never going to ask you this. I don't know this off the top of my head. I know by looking at it right now because I can read 1 over sigma times square root of 2 pi times e to the negative x minus mu over 2 times the variance. Now, if you do know some calculus, you can look at that integral and go, that's a hard one to do. It's got exponents in it. It's got the base of the natural log in it. It's a hard, that's a hard one to do. It really is. So you just take the integral of the function. So that sounds trivially easy. If you know how to do calculus, right? So let's pretend we can just insert the program to do calculus into you and just use a USB key in that slot in the back of your head. I just insert calculus in there, and then you go, oh, easy. So if I wanted to know the percentage of people that have an IQ between 95 and 107, I would take this integral and I would plug in 95 and 107 into where the x is, and I would plug 100 into where the mu is, and I would plug 15 for all the sigmas, and I could actually do this once I took the integral of that. When you take the integral, it gives you a different equation. One could theoretically do this. Sure, go nuts. But the funny thing is, did we ever teach it to you that way? Of course not. Right? We could make it a little bit easier, and this is a reason why we've turned everything into zeros and ones, into a standard normal distribution. Because in fact, if we make the mean 0 and the variance 1, in other words, we turn it into z-scores, the function is a little simpler. Now, it's simpler than it was. That's still not a fun integral to take. And again, if you've taken some calculus, you will look at that and say, that is not a fun one to do. That's one that's a bonus question at the end of a calculus test. It's like, try that one. You stupid kids, try that one, you idiots. You think you're smart?
What's the east?
E is the base of the natural logarithm. It's 2.718281828. Natural logarithm. Yeah, with pi. But it's a constant. It's just a constant like pi is.
Okay.
Yeah. Yeah, it's just a different constant. So the base of the natural logarithm.
Is that one E for Euler too? I can't remember.
I'm sorry?
Why is it E again? Is it just a random one?
It's because it was in, I don't know. I was going to make something up. I thought I had a joke. So, I honestly
No,
don't.
it's not for Euler. Never mind it.
It's because it was discovered by a guy named Eddie. I made that up.
He just already did A through D for other stuff, so he just used E for
It might be, yeah, it may very well be something that simple, right? It's just a constant, just like pi is a constant.
I get that.
Yeah, that's all you have to worry about.
Okay, good.
Is it higher?
So that's a bit of it. Again, if you've taken some calculus, you know that's a little bit of an easier logarithm. Integral take. It's still hard, but you can see it's simplified some because we've taken the mu and turned it into 0, and we've taken the sigma and turned it into 1. This is so what we've done basically is this. We've taken, that's the background of why we turn things into z-scores.
I like z-scores better.
Well, basically doing that, turning that equation for the natural, sorry, for a normal distribution with the mean of mu and the standard deviation of sigma into one with a standard deviation of 1 and mu of 0, that's actually what we've done. So
So
when we
that's
turn
what
it in,
allows us to do this
It's
instead
exactly
of the last
what-
equation?
the last equation is this. So it's turning everything into z-scores. Because remember now, we've turned mu into 0, and we've
Okay.
turned sigma into 1.
Yes.
So this is actually doing that in the deep math behind all this stuff is what allows us to do this very simple. This, in fact, right now in 21-26, I imagine, I think it's Thursday nights, Wayne teaches stats, and I imagine he is using a very similar example, except he's not talking about the calculus. So we find out the two z-scores, negative 0.32 and 0.466. What's the probability of between 0.32 and 0.466? It's 0.310. I'm not going to talk about how to look things up in a z table. You should know how to do that. And the chance of me testing you, right, you know, like, so, do this. How do I do that? So we standardize our data using the z-distribution to make it normal with a mean of 0 and a variance of 1. Because then we can look things up on a table. And that table tells us the probabilities. Okay. What? This doesn't have to be there.
One day I'm going to line up 30 chairs.
Yeah.
You'll know it was me.
Yeah, it's a funny joke. Yeah.
Put the clear podium right in the middle.
Exactly. Yeah. It reminds me of the thing Letterman did years ago, like 30 years ago. What happens when you put a mime inside a clear box, like actually put a mime inside a clear box? He doesn't just do this. He goes, let me out of this box. So someone actually did the calculus for you. That's the thing you have to think about. So when you look things up in those tables, someone actually did this calculus for you. Some graduate student, a very long time ago, before any of us were born, did the calculus for every possible value of z. Exactly. Every time you look something up in a table like that, say, thank you, unnamed student who gets no credit whatsoever, for doing this calculus for me. By hand. So now you just look it up in the z table. And by extension, we can look things up in t tables and f tables and chi-squared tables, etc. Because someone did all this calculus for us. There's also a nice web tool. I got a link there, but instead of following the link, I can just show you. And I'll show you in a sec what happens. There's the link. What this web tool allows you to do is literally just put in the variance, the standard deviation, and the scores, and say, oh, you want between those two, or you want just not those two, or what? And there's stuff like this all over the internet. This guy's website is great. David M. Lane, he does a lot of, he's a stats prof, and also knows how to write nice little software bits, so he put those two things together. So this is what it looks like on his website. Oh, look. Mean of 0, standard deviation of 1, between negative 0.32 and positive 0.466. And it tells you the error. Done. It's great. Now, you certainly can calculate it and play around with the z distribution or z table yourself, and that's no problem. But this is a nice way to do it as well. It also shows you a picture, which is great, because one of the things, and I think, I don't know how much Dwayne concentrates on this in 21-26, but I'll say that I think it's important to draw yourself pictures when you do problems like this. Because it should tell you should be able to look at that and go, oh yeah, that's looks right. It's about a third. Yeah, okay. A little under a third. Questions so far?
Dave, I have the same mean and the same standard deviation as you, but my between values are different. And my
I don't understand.
distribution looks different. That's what I want.
Your between values are different. Did you put them in?
No, I thought they calculated them for
You
me.
gotta
No.
select between.
You have to select between and then put the values in.
Why do you have to do that?
Because that's what you're asking. The question's asking you to do.
Okay.
Yeah. The question was asking you what.
So basically, the point of this is just to see the distribution.
Yeah, it
Okay.
sees it and then also calculates it for you.
Okay.
Yeah. Or you can do it with the Z table, which you probably learned how to do. Is what I know you
Yeah.
learned how to do in 2126.
Yeah.
Or you can do it. My calculator will do this for me
Okay.
because it has a Z function built into it.
Okay.
Right? It doesn't really matter how you get there. The point is, it's all doing it the same way. It's all doing it by, in the background, doing calculus. It's there. Okay. Shoes untied. I'm going to fall over. They're on the leg that kind of I kid. I kid because I love. First thing, honestly, every time I look something up in a statistical table, and when I do stats for my own work, I almost always do it by hand because I design simple experiments. Seriously. My PhD work had thousands of data points, but at the end, did a very simple calculation of these thousands of data points. For a lot of them, not all of them. Tens of thousands of data points. But very often with students, with my honors students, they do an experiment and we just sit down and do it by hand because it's like, or we could fire up SPSS and wait for it to boot and then try to, oh yeah, we got to set up the data set where I can say, what it means. Okay, here you go. Like it's not that hard to do. So I often do it by hand, then I look it up in a table, and literally every time I look something up in a Z table, a T table, a square, an F table, I think to myself, thank you whoever did the calculus for me, so I didn't have to do it. You should do that. So we look things up in a table or using a web tool or using SPSS or Excel does t-tests and z-tests. Google Docs, Google Spreadsheets does, they all do. So now we can do it that way. So none of this stuff I don't think is very scary. You were all taught this stuff, how to find the probabilities between two values. Now I hope you know why this works, not just that it works. You were told in 2126 to accept this because Pope Dwayne said it was true when you were Catholic. It'd be a great name for a Pope, wouldn't it be? Pope Dwayne? Yeah, it's a good name. Or a hat, big hat. Actually, he dressed up as the Pope for a Halloween party years ago. Anyway, it doesn't matter. Really good.
Do those pictures still exist? Do those pictures still exist?
I have them. They're on my Facebook. I'm not going to say that. Not mine. I know where they are because I think they exist. That's awesome. They're right. It's not anything embarrassing. It's a picture of Dwayne dressed up like maybe not, maybe a cardinal.
No, but it's something you gotta see still.
Yeah. Oh, I was a reporter, like in the 30s, and the whole night I talked like this, see? Let's see. Paul was Duffman, which was great. It was probably the best costume. So Paul was Duffman. What else? I think what other people were. Can't remember. Well, I do remember, but I'm just not telling you something. Nothing bad. Paul wouldn't mind if I told you he dressed up like Duffman. Dwayne wouldn't mind if I told you he dressed up like Paul. I'm not going to tell you anything.
Can you tell us what the costume was?
No, I'm not going to tell you anything. Because you might guess who it is, and then somebody will say that's an invasion of my privacy or something, and then, I don't know, I'll get sued by somebody. This is on the internet, it's open internet, somebody will sue me. So, this isn't scary, but now you know what. Questions about this stuff? Very often we're going to end early, and we end early because I know this stuff fills your brain, and you don't want to stop. All right, thanks everybody.